Welcome to my presentation of the paper Classic McEliece implementation with low memory footprint. My name is Johannes Roth. I did this work in collaboration with a colleague from MTG and also Juliane Krämer from the Technische Universität Darmstadt. Classic McEliece is known for its big public keys. So for the shown parameter sets, they are around 1/4 megabyte to over a megabyte. This is challenging for embedded systems since they often don't have many resources at their disposal. For our work, we use the shown Nucleo board. It features an ARM Cortex-M4 and 256 kilobyte of random access memory and 2 megabyte of flash memory. So while generating Classic McEliece key pairs externally and putting them on the device might work, it's not a solution for keys that need to be generated on the device itself, for example for ephemeral keys. In this work we address this issue, and more specifically we address the handling of the public key. That means we have two operations where the public key is used. For one, in the encapsulation operation, the public key is used, and also in the key pair generation operation, the public key is generated. However, the memory to hold the public key is simply not there on embedded devices. So we have to find a way to never store the full public key in memory. Our solution is to stream it. That means we only process small chunks of the public key at a time. This can be seen in two directions. So for one, a device that holds the private key needs to stream the public key to another party. And the other direction is a device that wants to perform the encapsulation operation, wants to process the public key while it is streamed in. In both cases, we do not want to store the full public key on the device itself. Our work is based on the round 2 reference code. That means performance is not optimized. Before we get into the details of the paper, let me first quickly summarize the Classic McEliece key pair generation and also what the public and private key are. The private key is generated in steps 1 and 2 and also 6. So in the first two steps, a binary Gopper code is chosen. This is done by generating the polynomial G and the support elements alpha. And in step 6, an mbed string S is also generated, but it's not important for this work. So basically the private key is a binary Gopper code. The public key is computed in steps 3 to 5. We can see in step 3 that the elements of the matrix are generated by the private key elements alpha and G. In step 4, a parity check matrix H-ad is formed. And in step 5, this parity check matrix is then transformed to systematic form. Systematic form means that the first n-k columns form an identity matrix. And this is an optimization for Classic McEliece because we can omit the first n-k columns since they are implicitly known. So the public key now is basically the parity check matrix, or more accurately, it's a part of the parity check matrix. Let us first look at the case where the public key is streamed from the device that holds the private key. So first, the approach in Classic McEliece is to compute the public key as part of the parity check matrix in systematic form. And the systematic form is computed by applying the Gaussian elimination algorithm. The drawback of this approach is that this also requires the memory to hold a complete matrix H-hat, which is even bigger than the public key itself. So what we do for our approach is we look at the problem from a slightly different angle. We express the result of the Gaussian elimination by the equation H equals S times H-hat. So this is actually the same as doing the Gaussian elimination, where S is the inverse of the leftmost n-k columns of H-hat. And realize at this point that S is also much smaller than h hat, since it's only the first n minus k columns. And with this approach, we can now compute the public key T in smaller chunks. Just take S as a given at this point. We will get into how we compute S later on. And also note that h hat can be computed on the fly from the private key. So for example, we can simply compute one column of h hat without storing the complete matrix h hat in memory, for example. I now show how the relationship of S and h hat can be used to generate single columns of the public key. So for all columns n minus k plus 1 to n of the matrix h hat, we can do the following. So first, we compute C as the ith column of h hat. This can be done from the private key. And then in the next step, we simply compute the product S times C. And this actually is the corresponding column of the public key. And then we simply send this product S times C, and we can release the buffers that contain S times C and C, because we do not need it anymore. So this can also be done in row major order or different orders, but in the case of row major order, we would need to recompute h hat for every row. This is much more inefficient, since with the column major order, we only need to compute each column of h hat one time. The public key retrieval algorithm imposes a significant computational overhead. So for the smallest parameter set, we need around 4 seconds, and for the largest parameter set, around 45 seconds on our Nucleo board. In order for the previous algorithm to work, we somehow need the matrix S. What we propose is to store the matrix S in the private key, and then call this new private key extended private key. And in exchange for storing the matrix S, we do not need to store the public key at all, because we can simply recompute it, and we can recompute it in a memory efficient way. Well, this approach obviously reduces the key pair size, but we still need to generate S somehow, and we also need to generate it in a memory efficient way, because if we require much memory, we again cannot compute S on an embedded device. The obvious approach to compute S would be to take the first n minus k columns of h hat and then apply the Gaussian elimination algorithm. If we do it like this, with the Gaussian elimination algorithm, this requires two matrices of the size of S, since we also transform an identity matrix to produce the inverse. So what we propose instead is we chose another approach to get the inverse of the first n minus k columns of h hat. We do it as follows. First, we set the inverse of S as the leftmost n minus k columns of h hat. So we can now store one buffer that contains the first n minus k columns. Now in the second step, we perform the LU decomposition. That means we find three matrices P, L, and U, such that the equation P times the inverse of S equals L times U holds. And you might now think that this is very inefficient, because we actually have now four matrices and all are of the size of S. But actually we can store the matrices L and U inside the buffer where the inverse of S resides. So we simply overwrite the contents in the buffer. The same does not hold for the permutation matrix P. We need to store it externally. But this can be done quite efficiently. So for our implementation, we need an array of 2 times n minus k bytes. So around, I don't know, 1.5 to 3 kilobyte, depending on the parameter set. And well, the This is the only non-constant memory overhead of the inversion of the inverse of S. So in the next step, we need to invert L and U. This is again done in place. So we overwrite the content of L by the inverse of L, and we overwrite the content of U by the inverse of U. This can be done since the structure is special, and the inversion basically amounts to backwards and forward substitution. Now in the next step, we compute the product of the inverse of U and the inverse of L. This again is done in place, so we write the resulting matrix inside the buffer where the inverse of S used to be. Again, we make use of the special structure of the matrices. And in the fifth step, we finally undo the permutation and obtain the matrix S, which can be expressed as the inverse of U times the inverse of L times P. Now we have described the direction where the public key streamed from the device that holds the private key. And now let us look at the other direction where we receive the public key from another party and want to perform the encapsulation operation. So first, what is the encapsulation operation, or how is the public key used in this operation? Well, the public key is used to compute the syndrome. So the syndrome is computed by multiplying H by E, where H is the parity check matrix with the first n minus k columns being the identity matrix and the rest being the public key. And E is a random weight t vector that has to be generated for each encapsulation operation. And the goal is now to consume all bytes of the public key that are received and update our intermediate result of the syndrome. It can be seen quite easily that this is how this is possible. So for the matrix vector multiplication, when you think about it, it's just a huge expression with many independent terms. And what we do is we simply compute the independent terms and add them to the intermediate result of our syndrome. I will explain it for an example. So in this example, we receive one column of the public key at a time. In principle, you can receive the public key in any order, and any size of chunk is possible to consume. But it's best explained with this example. So in the first step, we generate a random error vector E. As I said, this has to be done for every encapsulation operation. And in the second step, we set S to E. This is simply handling the first n minus k columns of the public key, not the public key of the parity check matrix. So the identity matrix is handled with this step. And then we handle all remaining columns of the public key. So for all columns of the public key, we first receive it from the peer. And then we simply update our syndrome, the intermediate result of the syndrome, by adding the ith element of E times C. This, in the binary case, this simply is that the ith element of E decides whether or not the ith column of the public key is added to the syndrome or not. A similar approach has already been described for the original McEliece scheme. We have not seen it mentioned for the Classic McEliece scheme yet, but we think it deserves some attention because it is very easy to implement. And for embedded devices, this can enable the use of Classic McEliece in scenarios where it was not possible before. It nearly eliminates all the drawbacks of the very large public key, aside from the network overhead. Let us now look at the memory requirements of the previously mentioned algorithms. So for the reference implementation, the memory requirements of the key pair generation is dominated by the matrix H hat. We need the complete matrix H hat in memory to perform the Gaussian elimination. And this means we need n times n minus k divided by 8 bytes. For our variant, the extended private key generation, we almost in place invert a matrix of the size of S. And this results in n minus k times n minus k divided by 8 bytes plus 2 times n minus k bytes. In this table, we can see what this means in actual numbers. So for the smallest parameter set, we can see that the reference implementation requires 334,000 bytes to compute the key pair, and our implementation only requires 75,000 bytes. So this is only comparing the matrices H hat and S, because this is the biggest factor, and also the 2 n minus k bytes for the permutation matrix. This means the difference in bytes for the smallest parameter sets is nearly 260,000 bytes, or a ratio of 0.22. For the largest parameter set, the reference implementation requires 1,700,000 bytes, whereas our implementation only requires around 350,000 bytes. The difference is over 1 million bytes, and the ratio is 0.21. This means with our implementation we can save a lot of space and still generate the Classic McEliece key pairs. Also note that our approach can also be used to stream the public key to flash memory. So the drawback of the approach is that streaming the public key requires a high computational effort, as I showed previously. It was like 4 seconds for the smallest parameter set. However, if we choose to stream the public key once to the flash memory, we do not need to recompute the public key every time we need to send it. But we also have the benefit that we do not require as much memory to generate the key pair as with the original Classic McEliece key generation algorithm. One thing to consider is that you might have limited write cycles for flash memory. So if you use very short-lived ephemeral keys, then you might wear out the flash memory quickly with this approach. So for the streaming encapsulation, what we really need to store temporarily is the buffer E and the resulting syndrome S. And also we have to buffer the chunks of the public key that we generate. For our implementation, we choose to buffer chunks of 8 columns at a time. This means n minus k bytes at a time. We assume that the public key is sent in column major order, as I've shown in the algorithms before. In principle, any order would be possible and any size for the chunks would be possible. While the memory overhead is ranges from 1,300 bytes to nearly 3,000 bytes. This could be nearly cut in half if you choose to buffer much smaller chunks. So to wrap up the previous results, we showed that one can implement Classic McEliece with much less memory than one might think, because you actually do not have to have enough memory to store a public key. And this is especially true for the encapsulation operation, because there, as we showed, you only need a few kilobytes of memory to perform the encapsulation operation, despite the public key being up to over a megabyte big. Furthermore, the streaming encapsulation might also mitigate some denial of service attacks. For this, imagine a scenario where a server accepts connections from clients, and the clients send Classic McEliece public keys to the server. In this case, the server has to allocate space for Classic McEliece public keys for every client. And an attacker could abuse this by opening many connections and never finishing the encapsulation operation. And the server would have allocated very many Classic McEliece public keys in memory, and the memory could be quickly flooded. For the streaming encapsulation, however, the server would not allocate as much space. Only a few kilobytes of space would have to be allocated instead of the whole public key. This is why the streaming encapsulation can mitigate denial of service attacks to some extent. And last but not least, we will now demonstrate the practical relevance of these results with a proof of concept TLS implementation. For our TLS prototype, we use the mbedTLS library, which supports TLS up to version 1.2. We integrated Classic McEliece in a cipher suite by using it as a public key encryption system to encrypt the TLS pre-master secret. The exact way is to encapsulate an AES key and then use this AES key to encrypt the TLS pre-master secret. This is the way one would use an RSA key. And the only difference here is that we use ephemeral Classic McEliece keys as opposed to static RSA keys. The parameter set that we chose is the smallest parameter set of the Classic McEliece scheme, because in this case the private key or the extended private key fits quite nicely in our memory. We use Sphinx Plus signatures for the certificates and also for signing the ephemeral public key. The signatures are 49,000 bytes large, and we chose this to demonstrate that we even have some space left to verify large signatures. The board can handle both sides, so we can run the server side and the client side on the board. And in the following, we will give measurements for completeness. Note, however, that the speed was not the goal of this work, so we used the Classic McEliece reference implementation, where we implemented our adaptations of the algorithms, and we also used the reference implementation for Sphinx Plus. The following two scenarios are considered. In one scenario, the board is the TLS client and connects to a TLS server, and in the other scenario, it's the other way around. And the other party is a much faster x86 machine, so it's an Intel i5 8400. Therefore, the computations on the other party do not play a huge role. So these are the average timings. First, the average timings for the board as a server. The total handshake time is 126.3 seconds, which is actually very long for a TLS handshake. But note that the Sphinx Plus signature, the generation of the signature takes around 109 seconds. So the majority of the time is spent on the Sphinx Plus operation. And the Classic McEliece operations are made up of the extended private key generation, nearly 11 seconds, the public key retrieval around 4 seconds, and the decapsulation around 1 second. Not included in this list are the network overhead for sending the data or receiving the data and the computations on the x86 machine. For the average timings of the board as a client, we have a total handshake time of 5.83 seconds. And the encapsulation operation is actually quite efficient, so it's only 0.018 seconds. Again, the Sphinx Plus operations make up the majority of the time, so it's 5.18 seconds. We actually have to verify two signatures, one signature for the certificate and the other signature for the ephemeral key that is signed by the server. Well, that was my presentation of the paper. So if you have any questions, please write me an email. You can also look into the paper and see if the question is answered there. Thank you for your attention.